Our next speaker is Mick West. Mick is the author of Escaping the Rabbit Hole, How to Debunk Conspiracy Theories Using Fact, Logic, and Respect. His new podcast, Tales from the Rabbit Hole, takes that book a step farther, discussing the effect of conspiracy theory culture on society and more personally with his guests. It is riveting, and you should be listening to it. He's been debunking extraordinary claims, alternative beliefs, and conspiracy theories for over a decade on his metabunk.org forum, and draws upon that experience in his book and his podcast. On a personal note, I've had multiple friends who I've discovered recently are deeply invested in conspiracy theories. At first, I thought they must be joking, but further discussion has revealed that these are actually deeply held beliefs. Mick's work has given me the tools to have an intelligent and effective and respectful conversation with them that has already had an effect on their unconventional and potentially harmful beliefs. There are few concepts more fundamental to the skeptical movement than convincing people of reality. And we've asked Mick here to talk about his experience with science communication and conspiracy theorists. Please give a warm welcome to Mick West. Are you turned on?
Oh, thank you, Jay. Very good. All right. I describe myself as a debunker, meaning that I investigate things, I investigate claims that I think are probably wrong, and they're usually claims that are related to conspiracy theories. When I've investigated them, I find that they are wrong, I explain why they're wrong. I've been doing this for many years. Over time, I've noticed a problem. A lot of my explanations rely on science and mathematics, which sometimes works, but most ordinary people, have a very limited understanding of science. And this is especially a problem for conspiracy theorists. Conspiracy theorists often think that scientists are part of the conspiracy. For example, people who don't believe in global warming think that the scientific establishment has somehow been corrupted by the powers that be into furthering this conspiracy. So how can we effectively communicate scientific explanations of things to people who don't understand or trust science? And today, that's what I'm going to talk about. And from a personal perspective, these are things that have worked for me, things that I've discovered over the years, and things that I've learned from my experience debunking things on my websites and in other places. First of all, let's define some terms, make sure we're on the same page, which is a very important part of communication. What's a conspiracy theorist? Well, a conspiracy theorist is someone who believes in a conspiracy theory, and we're all familiar with these types of things. A theory that explains a situation or an event as resulting from a secret plot from a powerful group. Now, a lot of people don't like the term conspiracy theory, most of the people who are conspiracy theorists, because they think it's derogatory. But I use it because I think it's a useful term which people understand what it means. Examples, JFK was assassinated by the CIA, the moon landings were staged, 9/11 was organized by the US government, various versions of that. There's a theory that planes are spraying chemicals on top of us. This is known as the chemtrails conspiracy theory. And people think that events like the Boston Marathon bombing was staged, or things like Sandy Hook. People think that these were actually staged events for some reason, like to try to alter society in some kind of subtle way by faking events which make us think certain things, or to try to take away our guns. Or there's the theory that Jim talked about just now, which is that the Earth is flat. There are actually quite a few people who genuinely believe that the Earth is flat. And I was actually at a Flat Earth conference a couple of weeks ago, and I spoke to a lot of them, and they do actually believe this. Science communication, what do I mean by science communication? Well, it can kind of divide this into two things. Science communication could be just science promotion, which is explaining what science does, why it's important, and encouraging science education, and trying to influence public policy to get more science taught in schools and try to get a better more investment in science and things like that. That's one aspect of science communication, and a lot of people do that very well. Another thing is science explaining, which is actually just communicating the results of science and explaining how they apply to particular situations or how they show that one thing is a certain way or another. Explaining the science to an individual. And I've got some examples there, which you're all familiar with, explaining how we know that vaccines don't cause autism, or how we know how vaccines work or how they do work, things like herd immunity and things like that. Explaining the simple physics of how carbon dioxide traps heat, how it actually acts as a greenhouse gas. Things like that are a science communication in the sense of explaining science. Now, I'm going to start my, my talk with a cautionary tale of a lesson I learned. We started last year in Berkeley at this event in Skeptical 2018, and I was sat at a group of table with a group of people, including Leonard Trammell. And we were discussing the topic of chemtrails. I think I brought it up. And the conversation turned to the topic of someone known as the Crazy Rainbow Lady. You may have seen this video before. It's been around for a very, very long time. There's no audio on this, but what's happening basically is a woman is sprinkling her lawn, and she notices a rainbow in the sprinkler. And she starts going on about how she's never seen this before, and how the government is putting chemicals in the water, and this is obvious proof of the government messing with the environment. It's kind of a well-known video. It's actually from 2008, so it's over 10 years old now. And we talked about this thing, and everyone laughed about it. And Leonard said, "I bet there's no more than 2 people at this table who understand how rainbows work." And I went, "Ooh, I'm one of those people. I know how rainbows work," because I've been looking into things like rainbows and halos and things like this because I did a lot of work with chemtrails, which is this type of thing, and they often point at these things, and so I'd studied them. And I said, "I'm one of those 2 people." And Leonard looked at me and he said, "Really? You really think you know it? Because it's actually quite complicated." And then he started talking about some things to do with how rainbows actually work, and I kind of realized that, well, maybe I don't exactly understand exactly how rainbows work. And the conversation kind of moved on. We started talking about other things, but this little exchange kind of bothered me. So when I got back home and over the next few months, I occasionally would look up how rainbows work and try to figure it out. If you go onto Google and you ask how rainbows work, I just did an image search here for how rainbows work. It gives you all these nice little images. You get these various images of water droplets reflecting sunlight and refracting sunlight and splitting it up into these different rays and the different colors. It's very straightforward, so obviously there is an explanation for why rainbows work. Sunlight comes in, it gets bent a bit, it gets reflected off the back of the raindrop, and it's spat out the front into a rainbow. That kind of glosses over a variety of points. For example, in this diagram, you'll see that the top of the rainbow here is red and the bottom is blue, but when this is coming out here, it's blue on the top, but it's red on the bottom. So you show people this and they go, well, this rainbow's upside down, what's going on with this? So this little explanation is already a little bit confusing. And why is the sunlight only going in this spot here? What about the sunlight that goes in all the other spots? It's just kind of a little bit confusing. So when you actually get into it, it's a little bit more complicated than you initially think. Raindrops in different positions reflect different colors of light based on their angle. For each angle of incidence of the sunlight, there's a specific angle, a minimum angle at which it will reflect one particular color. So this means that the drops that are higher up are reflecting red light, which comes down to you, and the drops that are lower down are reflecting the blue light, and you've got little drops in between. So you get this little band of colors, which is actually coming from different drops of rain. Each one of these are blue drops, these are green drops, these are yellow drops, these are red drops. So it's more complicated than it seems. This was stuff that I kind of understood, and this was about where my level of understanding is starting to get a little bit shaky. So, that explanation describes the angles and the colors, but why is light even bending at all? Why does light bend in glass? There's a law called Snell's law, which you might be familiar with. If you've done a little bit of high school physics, you might have heard of Snell's law. Snell's law tells us that the amount of a bend of a ray of light is related to the refractive index of the 2 mediums. So you've got some air, which is a specific refractive index, and you've got water, which has a different refractive index. And there's this little equation here, very simple equation, that tells you how much you're going to bend. But why is it bending? Well, it turns out there's another principle you've got to learn about, which is called Fermat's principle, which tells you that the water tells you that light always takes the path which takes the shortest amount of time to get from one point to another point. And you'll often see this explained in terms of an analogy. The analogy is a lifeguard sees a person drowning out in the ocean. Now, there are ways along the beach, and they're out of it. So the lifeguard, if he was to just run straight to the ocean and swim to that person, it would take quite a long time, because you've got to swim a long way. If you were to run all the way along until you were parallel with this person and then swim straight out, that would be a lot quicker, but it's still not the shortest path. The shortest path is actually running somewhere like 85% of the way along and then swimming the rest. This is the analogy that's most commonly used for explaining Fermat's principle. But it didn't make any sense to me. You know, why does light take the path which takes the shortest amount of time? It's like, does light know that if I go this way, it'll take less time than going another way? You know, light isn't an intelligent being like a lifeguard. It's just this thing. So it turns out there's another layer on top of that. There's a more complicated layer, which is called the Huygens-Fresnel principle. And that says that light, a wave of light, is made up of lots of tiny little waves, which are all kind of combined together into kind of one big wave. And at every single point on that wave, there's lots of little waves, and they all go off in all different directions, and then they all interfere with each other, and you get a new wavefront. Sounds kind of confusing, but there's a little animation here which kind of makes it a bit clearer. This is a wave of light coming down towards a medium, and as it hits this medium, it kind of creates these new waves, and then the edge of all these wavefronts at the bottom is now at a different angle to the wavefront before. So this, you know, in theory, is explaining what is going on, and explains why we get Fermat's theorem and why we get Snell's law. But again, why is light actually slowing down? Why is light slowing down in water? So I discovered this guy, Dr. Don Lincoln, who's got some very good videos on YouTube. I recommend them if you want to try to understand these things in greater depth. Why does light actually slow down in water? Well, first of all, he tells us that there's a lot of wrong answers that are bouncing around on the internet. And this is a very big problem in science communication. When things get complicated, people try to simplify them. And they often try to simplify them in a way where they essentially are inventing answers. They're creating answers. And then these answers get put on YouTube, and then they're going to get repeated and repeated. One of the reasons people might say that light is slowed down in a medium like water or glass is that it's bouncing around. It has to take a longer path to get from A to B. And that kind of makes sense when you think about it. You know, if it's got to go all around these corners to get from one side of the piece of glass to another, it would make sense that it slows down. But if that was actually happening, what would happen was the light would spread out. And we know that you can shine a laser beam straight through a piece of glass, and it's just fine. It doesn't spread out. Another explanation that is given is that when light hits an atom in a material, it absorbs the photon and then retransmits that photon. This is an explanation which is given on some physics sites as for why light slows down in glass. But it turns out that's wrong as well, because if light was absorbing and retransmitting photons, like in these little things here, if it was bouncing around, there's no real thing that controls what direction the light actually goes in. So those are the wrong explanations. And so Dr. Don eventually tells us the correct explanation, or so he says, which is that light is an electromagnetic wave. We all know that light is electromagnetic radiation, part of the electromagnetic spectrum. And when light goes through a medium like glass or like water, which is transparent, it actually excites the electrons in that medium. And these electrons themselves make electromagnetic waves, make a different electromagnetic wave. And then when you add these two waves together, a principle called wave superposition, it creates a new wave, which is a little bit slower in transmitting photons than the original wave, which is why light slows down in a medium. Yeah, I'm kind of getting a little bit lost now. Some of you might be getting a little bit lost here. It's all getting quite complicated. Then he kind of ruins things for me by telling me we can't actually use Huygens. Huygens doesn't actually work, he tells me, because there are actually a whole bunch of wavefronts that come out from the Huygens principle, and they're in all different directions. and this would create lots of waves of light going in different directions. And I don't know if this is correct, but he's got a PhD in physics, so I have to trust him. He says instead of using Huygens, we have to use Maxwell's equations, which are something else, which is getting even more complicated. You see, we've got some funny little symbols here, which you only understand if you actually take advanced physics. And I've got no idea really what they're doing. They're not very long. They're quite short equations, which is good. But it doesn't really help if they're short if you don't understand what the letters actually mean. Because the upside-down triangle is delta, I think. No, I don't think it is. That would be the right way up triangle. But anyway, so then he gives me this very, very simple explanation, which is that there's two vectors of light, one perpendicular and one parallel. The one that's parallel stays the same, and the one that's perpendicular gets shorter. And this is because of Maxwell's equations, but I don't really know how. I don't really understand it. So I'm completely lost at this point. And then he tells me that the real explanation for why light slows down in glass and why light changes direction and why light splits up into different colors, which is something I barely touched on here. It splits into different colors because light slows down at different rates depending on the wavelength of light. But the real reason is because of quantum physics. And quantum physics is something that I have no idea. I really have no idea how it works. And I would imagine most people here have no idea. I think there was a famous quote someone said, if you think you understand quantum physics, then you're lying to yourself. Because no one understands it. Perhaps Richard Feynman might understand it, and obviously the real physicists out there probably understand it. But for the average person, this is way too much explanation. So I think this was actually summed up by Richard Feynman in a famous talk he gave, which wasn't titled "Effing Magnets, How Do They Work?" But that was the gist of the talk. What happened was a journalist asked him how magnets work, and the journalist said that when you push magnets together, they attract each other if you do north-south, and if you turn it around and you do north-north or south-south, then they push away from each other. And so he asked Professor Feynman, how does that work? What's actually going on there? And Feynman kind of went through a little bit of what I went through just now, kind of saying that there are different levels of understanding of what you can, how you can explain that question. But he kind of summed it up with one saying, which was, I'm not going to be able to give you an answer except to tell you that they do. And what he's saying there is really that he recognized that the journalist didn't have the basis of science for understanding the full explanation. Like, I don't understand quantum physics. So if someone tried to explain to me why rainbows work in terms of quantum physics, I wouldn't understand it. I don't have that good an understanding of Maxwell's equations, so that's not very good either. And I don't really like a lot of the other things. But I do have a certain level I can understand things at. And I know that rainbows do happen. With magnets, there's lots of science of magnets where we can explain what actually happens with a magnet. We can measure the Gauss, the field that they have. We know what will happen when we do certain things with electromagnets. We know different materials have different magnetic properties. We can know all these things, all these aspects of science, without actually having to explain why these things are happening. Feynman tells you that you can't give an answer for the why, but we can actually show that these things actually do happen, and we can tell you that they do. So, do I understand rainbows? Was Leonard right about me understanding rainbows, or not understanding rainbows? Well, I don't understand the quantum physics behind rainbows. I understand Maxwell's equations a little. They look kind of familiar to me, but I don't really understand them. Huygens' principle, I sort of understand that. Fermat's principle, I sort of maybe understand that. I don't really like it, though. I don't really like this analogy with the swimmer and the lifeguard. It doesn't make any sense to me. Snell's law, I understand the math behind it, but it doesn't really explain why. Getting back to the simpler explanations, sunlight on raindrops, the angle of minimum deviation, it's all very reasonable explanation. And yes, I think that's actually something I do understand. But the very simplest explanation of a rainbow is that rainbows are a reflection of light from raindrops. And the raindrops split the light into colors, and that makes a rainbow. That's the explanation of a rainbow that that's the explanation that most people will understand. What this rainbow experience taught me? Well, first of all, Leonard knows a lot more physics than I do. My confidence at the pub was misplaced last year, and I apologize, Leonard. And most people will never really understand rainbows. Most people won't get beyond the very basic level of understanding of how a rainbow works. The physics of a rainbow working, you kind of know, what's going on, there's reflections, but you don't really know. Most people won't ever know. And explaining why something happens is really a rabbit hole. If someone starts asking, why is this happening, and then you start trying to explain it in terms of actual physics and what's actually going on and getting into these why explanations, and then why is that, that's a rabbit hole. You're going to very quickly get into territory that either you don't understand or they don't understand. Hopefully it's going to be something that they don't understand first, but it's possible that you'll run out of your own understanding and you'll get lost. So it's much better to focus on the what and the when of a situation. What makes a rainbow physically? It's rain, it's sunlight. When does it happen? It happens when the sun is behind you. Don't focus on the how and the why. The why is something that you're not going to be able to explain to people in a timely manner. So what should we tell Sprinkler Lady, crazy Sprinkler Lady? Well, it turns out actually she was a crazy person. She wasn't just a stupid person. She was someone who was deeply mentally ill. She was someone who was paranoid schizophrenic. And she has a large number of videos on her page about how the government is beaming radio waves into her head. So it's kind of sad that she became a figure of fun over the years. And she posted these in 2008, and she hasn't actually posted anything since 2010, so I don't know what actually happened to her. But if she was here, what would I tell her? Well, I would tell her the what and the when, and not the how and the why. I would give her the very, very simplest explanation, how a rainbow forms. This is the simplest explanation I could actually found. It's just, there's a sun, there's a person, there's some rain, and there's a rainbow. And this is what happens. And this is the explanation because this is what we know. We wanted to make the simplest connection possible between this explanation of a rainbow, which you will probably agree with, and what she sees in her garden, seeing this what she thinks is a suspicious rainbow-like shape in her sprinkler. The connection here is that rain is made of drops of water. The sun on drops of water makes a rainbow, and sprinklers make drops of water, and the sun was behind her when she saw this rainbow. So if you give her the simplest explanation possible in terms of a scientific explanation, this isn't very scientific, it gives you the very loosest possible explanation. This is what's actually going to be the most effective to start off with. Now, she might also wonder why this rainbow was so brightly colored. And I think, perhaps in this instance, it was because there's a dark fence behind it. So yesterday morning, I did a very quick experiment where I went outside and made a rainbow of my own. And this is a little bit washed out. It's hard to see here, but it's going to wash out here. But when you get into this darker area, it becomes a lot more brightly colored. And it could just be that she never actually had a sprinkler in the garden in that position before with the fence behind it and didn't notice that you get this very, very bright rainbow when it's over a dark background, and you get a less bright one like when it's over a light background. So a very simple demonstration like that can be actually helpful in communicating these things. And that's something I just did in like 5 minutes in my yard yesterday. So how do you talk to conspiracy theorists? How do you talk to conspiracies about science? You've really got to tailor it to the individual. Each person's going to be different. They're going to have a different level of understanding of science. And if you don't know what that level of understanding is, then you've got to start at the bottom. And you've got to try to figure out what that level of understanding is. Start with the very simplest things. You've got to try to determine what you know and they also know. What is the common ground? What are the things that you both agree on? What is the basic points of science that you agree upon? And from that, what are they missing? What are the things that they not necessarily don't understand, but they don't know that actually happened? Like some people might know that rainbows only happen when the sun is behind you. Some people might have this idea that rainbows only actually occur when the sun is shining and it's raining, but they don't know that it happens when the sun is behind you, and so they won't get this connection. Sometimes the things that people miss in science can be very, very, very simple things. They don't have to be complicated things. So you've got to get down, down, down to the simplest thing. Keep it as simple as possible, but no simpler. You get the most bang for your buck if you can use an explanation which is sufficiently complicated, and yet they will still understanding. You've got to leverage their existing knowledge as much as you can. Don't over-explain. That talk I just gave on my understanding of a rainbow is a good example of over-explaining. I gave you way too much detail. I went into topics which I didn't really understand, and most people here don't really understand. Yeah, I was doing it to illustrate a point. But if someone was going to ask why do rainbows work, and you start talking about even Maxwell's equations, then you've already lost the discussion there, especially if you get into quantum physics. Show, don't tell. This is a favorite saying of mine. And this is basically, use demonstrations, don't use explanations. Demonstrations will show somebody something. You can say, oh, here's the sun behind me, I'm going to spray this hose here, and you see a rainbow has formed. If you tell them that the rainbows only form when the sun is behind you, it goes in one ear and out the other. But if you actually show it to them, it's going to stick, and they're going to comprehend it. Keep the science at hand. Just in case the person is receptive to science, it's a good idea to be able to have the science ready to roll out and actually show them what's actually going on. All right, some more examples of this type of thing. This is a related example, and this is a thing called a chembo, which is, it kind of looks like an upside-down rainbow, which is, it's not what it is exactly. It's actually part of a solar halo. But chembos are famous in the chemtrail community as being evidence of a secret spraying program. People think that the government is secretly spraying things in the air, and it's altering the atmosphere, and it's making these chembos appear in the clouds. And this is the description that they give: a rainless rainbow caused by diamond dust, aluminum oxide, and barium spray chemtrail geoengineering. And yeah, as I said, it's actually part of a halo. It's actually this bit up at the top here, which is called a circumzenithal arc. And from that description we just had, let's go back to that, the rainless rainbow actually establishes some common ground. The guy knows that you need rain for a rainbow. So you've got a little bit of some kind of understanding of where he stands in terms of physics. But you've got to ask him now what's actually missing in his knowledge. What's missing is his knowledge of halos. Halos are made from ice clouds. Contrails that you see, the clouds that are formed behind planes are also made of ice cloud. In fact, they are ice clouds. They're almost exactly the same. Often when a contrail spreads out, it will form a layer of cloud very similar to this, and you will see things like these halos in it if the sun's in the right position and if it's the right type of ice crystal. Contrails, halos form around the sun. Now, a rainbow forms opposite the sun. The sun has to be behind you when you're looking at a rainbow, but when you see a halo, you have to be looking at the sun to see it. So it's a different type of thing. So you can show them how this explanation fits what they're seeing, in a very literal way. There's the actual thing that he took, and here's the actual arc at the top. You can show them that it fits this, and that this is something that you see in all kinds of science books, and it's true, and it's not something that is new or would be the result of chemicals in the air. Don't over-explain it, though. Don't get into all that stuff about quantum physics. You don't even have to tell them about refraction. You have to show them that this is actually something that happens. This is the first step of science, is observation. And these people are a little bit before this first step of science. So you've got to get them to observation. You've got to get them to observing the fact that halos actually happen. And maybe later you can explain to them why halos actually happen. But have the science in the background if you want to get into a deeper thing. There's a great site called atoptics.co.uk, which has wonderful explanations of all these different aerial phenomena. And here's their explanation for the circumzenithal arc. It's actually the result of these hexagonal crystals floating in the air up above where the sun is, blah, blah, blah. Complicated explanation, but it's there if you need it. All right, the next example is the oily chembo. which is like the Kembo, but it's a different set of colors. You know, regular Kembo looks just like a rainbow. It's got the nice primary colors, but the Kembo, I don't know how well you can see that here, but it's actually kind of more of a smear of colors. It looks kind of like oil looks like on a pavement. And they describe it as being this intense oily spill looking type of cloud that's in front of the sun with a heavy aerosol layer, blah, blah, blah. And they say it looks oily because it looks like oil. It does actually look like an oil spill. If you look at this set of colors here, they're actually very similar to the set of colors you're seeing around the sun. So it kind of looks like it's some kind of oil spill in the sky. It's not, of course. It's actually a normal, natural phenomena, and you can explain that. But it's useful to look at all three different ways that we can get some kind of color spectrum in the sky, rainbows. There's refraction, which actually happens two ways, like forwards and backwards. There is diffraction, which is what is causing this cloud iridescence, which is the oily clouds that they were seeing in the previous example. Also causes a thing called a corona, which is this circle around the sun. And then there's interference, which is what's actually causing the colors on an oil film or on the surface of a balloon. These are very, very different phenomena, but they are also very closely related. Diffraction is light bending around things. If you've got very, very small particles in the air, the waves of light, when they bend around it, will kind of spread out using Huygens' principle again, and they will interfere with each other, and they will cause these little bands, and then different colors and different wavelengths do different amounts, and there's these little graphs. Yeah, again, getting into things I don't really understand. Thin film interference, which was the oil film thing. What happens is with an oil film is that you've got the top of the oil and you've got the bottom of the oil, and they're only separated by a few molecules sometimes. And so the light going in bounces off the top and it bounces off the bottom, and you get this kind of constructive and destructive interference of the wavelengths, and you get all these different colors. So you get all these very reasonable scientific explanations, and I'm sure most people here follow the basics of this explanation. But how do you actually explain this to the conspiracy theorist? The conspiracy theorist isn't going to listen to your complicated explanation of science. They think that there's strange clouds and they're artificial clouds that they've never seen before, but are they actually? No, they're not. Can you explain it to them in terms of physics? Yeah, you could. Or can you show them something? Well, it's kind of difficult to show the effects of iridescence in clouds because they're up in the air, and it's hard to make clouds in your living room. You probably could, but it's a tricky thing to do. So an approach I found that works really, really well is showing that phenomena that people think is new is actually a phenomena that exists in history. And in this example, we have solar halos, and here's a woodcut print, I guess, from the 1500s. And it's showing one of the earliest depictions of a solar halo, the top half of one, and two what are called sundogs, or parhelia, which are these little kind of little sideways rainbows that you see sometimes at the side of the sun. And this is another famous painting also from the 1500s of a whole bunch of different things. And then there's lots of books, lots of old books that actually describe halos and coronas and how they work. And there's drawings of them from halos around the moon and coronas around the moon. So there's all these old things. There's these things have actually been seen for thousands of years. Aristotle discussed them in his book Meteorology. And you can use more recent books that have color photographs. Here's an example of a corona in the upper one and similar things in the bottom. You can show them that these things existed before, and you show them that an explanation exists for what they're talking about, and you can show them that it's not actually new. This is a book I have, I think, from the 1960s, and it's showing a circumzenithal arc, and you can show them that it looks more or less the same as what they've seen. And this is actually quite an effective technique. I've used this with the chemtrail people. Chemtrail people often think that chemtrails, the contrails, the lines of cloud that form behind planes, should not persist. They will say things like a normal contrail will only last for 30 seconds. So what I did was I got, over the years, I've accumulated a large collection of books on clouds and the weather. And I made a video of me going through each one and going to the page on contrails and showing them that this was and the description of contrails actually matched what they were seeing. It actually worked very, very effectively. A lot of people have told me that this was the one video that they helped them out of the chemtrail conspiracy theory. So this type of thing does actually work. And here's another one, the cloud iridescence. Obviously what we're seeing here is even more oily than what you see over here, but this is from some textbook from the 1970s. So it's showing them that a phenomena is real is a significant part of the journey. They don't need to understand the physics, and they're probably not interested in that physics. They just need to see that it's not new, and it's been in books for hundreds of years sometimes. All right, switching gears slightly, we're going to talk a bit about flat Earth. I was at a flat Earth conference 2 weeks ago. It was kind of a weird event. I'm not entirely sure how I ended up there, but somehow I ended up being a speaker at a flat Earth conference. And I was actually debating somebody, and it was one of the guys who was in that video that Jim showed you, Nathan Thompson. And I was talking to him about, we were debating on stage what his proofs of the flat Earth were. Excuse me. And one proof of the flat Earth that he gave me was a thing called the green flash. Now, a green flash is an atmospheric phenomenon. When the sun is setting and you've got a certain amount of refraction in the atmosphere, you see this little green flash at the top of the sun just as it's setting. It's a really cool thing if you ever see it. It happens relatively frequently, but you need to have a clear view of the horizon, which isn't that common on this coast especially. But you will see it if you look for it. It's a real thing. Now, he was saying that because light bends in this way, this is light bending down. Because when light bends down, red is at the top, and on this, green is on the top, and the blue actually gets filtered out by the atmosphere, so we only have green, yellow, and red in this. The green is on the top. He was saying that meant that light was actually bending upwards, which means the obscuration of the sun was due to refraction because the light was bending up and down, so some of it hits the ground and some of it goes up and misses the sun, so it gives this optical illusion, and that was proof that the Earth was flat. So I realized from the stuff I've been looking into about rainbows that this spectrum is actually upside down from how you perceive it. The green light is bent more than the red light, which actually means it gets raised up more. So in fact, green on the top proves that the Earth is round, if you're using his logic, which is kind of simplistic. He glosses over a whole bunch of things about how the sun actually doesn't change size and things like that. But he's using this one argument. So what I did during the conference is on the first day, I gave him one of these, which is a little prism, which is I black out one side of it, which if you ever want to try this experiment, it's a very good idea to black out one side. It makes it a lot easier to look through. And I also had a fake sun that I brought with me. And I showed him that if you look through the prism in the same way that you're looking through here, then you actually see red at the top, and you see green at the top, not red at the top, which means that light actually is being bent down and not up, which is the opposite of what he was saying. Now, this didn't take. This was the same guy that was kind of shouting at Nathan about, how you've got to look up at the sky, and if your feet are on the ground, why are you looking up at the skies? It's that guy, Nathan Thompson. He was a very hardcore guy. And in fact, when he came to give his speech, he actually took the prism that I'd given him and got an audience member up, and he held the prism upside down, which is kind of cheating, and he made the light bend the other way, and the woman said that it was red on the top. So he kind of messed that up. And then I was showing lots of people this experiment after the conference, and Nathan came by at one point, and I said, Nathan, look up the prism, look up it carefully, it's the key to everything. And I said this kind of dramatically to him, just to try to get him to look at it. And a few days later, this was me on stage, a few days later, he said, I will admit you got me thinking about the green flash argument I've been using with this prism you gave me. I'm going to test it more. Now, this is a major, major victory. This is a guy who doesn't give an inch. He never admits he is wrong. And by pestering him in person at this conference, I actually managed to have this minor victory with him. I don't know if it'll go very far. He'll probably come up with some explanation as to why his argument was wrong. But for people who are stuck down a rabbit hole, they get out very, very slowly and very, very gradually. And just getting that first step out of the rabbit hole, I think, is a victory. I don't hold out much hope for Nathan because he's very far gone, but there are other people at the conference who were less far gone, and I showed them the same demonstration, which they didn't really hold much stock in it anyway, but they showed them that Nathan was wrong, and then he admits he's wrong. It's a little step. All right, switching gears again. I tried to cover all of the sciences in this talk. Well, all three sciences that I was taught in school, which were physics, biology, and chemistry. So we're going to go over examples from all three of them. The biology example I'm going to talk about is blood. What color is blood? Blood, you can see there, it is fairly darkish red, very dark red in this example. And you can ask what color is it? Is it carmine, burgundy, chili red? One thing you can say, it's definitely not candy apple red, which is a very, very bright red color. Then we get to the Boston Marathon bombings of 2013. My father-in-law was actually at the Boston Marathon bombing. He was about 5 minutes behind when the bombs actually went off, so he could quite easily have been caught up in it, so it's kind of a personal thing for me. But I'm not going to show any photos of the blood from this scene, but there are several photos that were taken where you see a lot of blood on the ground, and it looks very much like candy apple red. It looks like it's paint, like someone just spilled a big bucket of paint on the floor. And the conspiracy theorists think that because you've got this blood that looks like paint, then it means that the entire event was staged. So there's some science behind this. And again, you could go into the science of it. The blood color depends on how much oxygen is in the blood. The dark blood, which is the blood you would see if you prick your fingers, is called the venous blood, and it's low oxygen, and it's dark red. The bright red blood is the arterial blood, and it's blood that's got a high oxygen content. And you get it from major wounds, like if you're shot through the heart, for example. So it's not something that people see on a daily basis. We're familiar with the little cuts that we get, but no one here is really that familiar. Well, probably some people are, but most people are not familiar with major wounds, like people getting their legs blown off. So it's a very unfamiliar color. So how do you communicate this to people? Well, there's lots of resources you can use. You can show them Wikipedia. The Wikipedia page for blood actually has these different colors of blood right up there on the main page. But suspicious conspiracy theorists might think that Wikipedia is part of the problem. You could look at books on hematology. Now it's got the same kind of problem that we don't really people don't know why they don't trust scientists, basically. But something I found was that deer hunting books actually have descriptions of why blood is these different colors. All right, moving on. That's enough about blood. Makes me a little bit queasy thinking about it. All right, physics. We're all familiar with Newton's laws of motion. Action and reaction are always equal and opposite is the third one, and everyone's very familiar with this particular one. And this is something that 9/11 truthers are often spouting out. They say that Newton's laws of motion were broken by the official explanation of the 9/11 conspiracy theory. And they point to diagrams like this that will say that there's a small mass on top of the building, and there's a lot, and then that destroyed, the small mass on top destroyed the large mass below. And that leads to things like this. This is a guy who's actually the head of Architects and Engineers for 9/11 Truth, which is the biggest organization. They've got like $1 million a year budget. And he's giving this demonstration of how Newton's laws have been violated, which is utterly ridiculous. It proves absolutely nothing. Cardboard boxes are nothing at all like the collapses of the Twin Towers. But he actually thinks he's demonstrated something there. The problem, of course, is that he is oversimplifying. And this is a situation where the physics is actually a lot more complicated than they realize, but they're just stuck at this low-level explanation. They think that there is the small mass at the top and there's large mass at the bottom. But really what we've got millions or perhaps even billions, or certainly tens of millions of tiny little masses, actually quite large masses like girders and whatnot. And they're falling apart in this very, very complicated way, which you cannot possibly make an analogy with these cardboard boxes. So this is a very difficult thing to convey to people because people don't really like to think about these complicated things because there's so many things involved. So I tried to simplify it, but also demonstrate something of what's actually going on. So I did this model in my garage. I made an 8-foot-high model. This is the bottom section of it here. And I'm demonstrating how stable it is, relatively speaking. You can throw that wrench at it, and you can see I can pick up a section of it, and it doesn't fall to pieces. It's all relatively solid. And I put the top section on. Takes me a couple of goes. I try to make it similar to the construction of the towers with a central core and some floors and an outer thing. And then I just displace the top, and the whole thing collapses. This is actually essentially the physical principle of the collapse of the World Trade Centers. The top started to collapse. The columns were no longer aligned with each other. The mass of the building fell through the floors, which don't actually support the building structurally. The floors were stripped away from the columns, and the entire building collapsed. So this is an example of how a demonstration is much better than an explanation. A lot of people will laugh at an explanation like this because it's just me with some wooden blocks, but it does actually work with people who are on the fence, and it can get a step in the door with people who are a bit further along. Chemistry, the last of the three sciences I'm going to cover. This is a bumper sticker you can buy on Amazon. It says, aluminum, barium, strontium, we do not consent. And it's showing a plane apparently spraying aluminum, barium, and strontium. And you can buy it on Amazon. The chemtrail people do tests of things like soil and water, and they test them for aluminum, barium, and strontium because they think this aluminum, barium, and strontium, for some reason, are a signature of a secret geoengineering program, which is what this spraying is all about. And you see this guy here has done a test, and he's found very high levels of aluminum and fairly high levels of barium and strontium in his pond. The reason they're finding these elements is that these are common elements in the Earth's crust. And what they're missing here is the fact that aluminum isn't actually found in nature in the metallic form. You have to extract it from rock. So when you talk about aluminum in nature, you're actually talking about rock, things like this. Rock, this is sandstone, which has got a whole bunch of different components, but a lot of those components are aluminum. So if you test the soil or the water or the air, you're going to have a bit of dirt in it, it's going to have aluminum in it. You can show them things like this map of the United States, which shows how much aluminum is in each area, and California is really high in aluminum. If you take a sample of the soil, it's typically around between 5 and 10% aluminum in its rock form. So you can try to explain to them what's going on here, this difference between aluminum and the metal and aluminum, the compound. But this is something where it gets kind of confusing. And I was looking at things on the internet. What's the difference between an element and a compound? And I found like people were saying, molecules are one thing and compounds are another thing. But then they're not saying that compounds are also molecules. Only half of the sites that give these type of explanations give ones that are as good as this one, which I'm sure has some flaws as well. But it gets very confusing for people. You all might think that it's very straightforward. You know what a molecule is. You know what an atom is. You know an element is just atoms of that type of element. And you know that molecules can be lots of the same element, or they can be two elements joined together with atomic bonds. So a lot of you will know this because you're fans of science. But the average person does not really understand this at all. They've got really no idea what's going on. They don't really have a knowledge of the difference between what a compound is and what a mixture is. So I tried to make the simplest explanation possible, and I gave this little meme, which is basically saying, this is a metal, aluminum, it's made of atoms. This is rock, aluminum, it's made of atoms of aluminum and some other atoms. And this is the test that they use on that thing I showed you earlier, and it measures atoms. So I just bring it down to the simplest level possible. It's measuring atoms, so it finds the atoms of aluminum in rock. Simplest thing possible. You could also show them the proportions of aluminum and other things in the Earth's crust, and show them that what they're doing is they're simply testing for 3 things that exist in the Earth, and that the ratios that they found are about the things that you'd actually find in the Earth's crust. If they tested for anything else, they would find these other things in that proportion as well. You can also show them that aluminum, barium, and strontium are very common ingredients in fireworks. This is something that surprises a lot of the chemtrail conspiracy theorists because they think that these are toxic poisons that are killing everybody. But I know you see them on 4th of July every night, especially aluminum, which is used in sparklers. So, sum it up. Science education would be great. It would be great if you could actually teach people all these things, and if we taught people more things about science in school, that would be wonderful. But it's not practical in a timely manner for talking to conspiracy theorists. Showing, not telling, is a key part of talking to conspiracy theorists. Your verbal explanations, your written explanations, they go in one ear or in one eye and out the other. But if you can actually show them a demonstration, it's a lot more effective. Explain the what and the when of things, not the how and the why. Why is just a big rabbit hole. And keep the science close. And use as much as is possible, but don't get too deep into the weeds. Keep it in reserve, tailor it to the individual. And this approach, I have found, does actually work. I've talked to lots of people who tell me that the demonstrations that I've done and the videos that I've made have actually made a difference, and there are people who actually are now no longer conspiracy theorists. So there is hope. We can actually help people out of the rabbit hole. Thank you.